All right, you guys, topic 3 is all about transformations, and 3-1 is about specifically reflections. So on page 101, we're going to take a couple notes before we get started with what a reflection is. So the concept. A reflection is a transformation, so a movement, that reflects each point in the pre-image. Pre-image is what we call our starting image, across some line of reflection. And it's pretty much just like a flip. Like you have a reflection in a mirror where it flips your appearance around. There's properties of reflection, and you're going to see in this little diagram that we've got triangle ABC, and it's being reflected on this blue dotted line M. And you can see that point A is on the line. So A and what we call the reflected point, A prime, this little tick mark means prime. A prime are actually the same point because it was on that reflective line. Now what you're going to see is points like B and C are not on the line. So line M is what we call the perpendicular bisector, aka the line that connects a point and its reflective point is perpendicular to that line of reflection. But one of the main things we need to know is how to write that. So we would say the reflection of ABC across a line M can be written as capital R for reflection, sub M, R sub M, which means reflection across line M, parentheses, triangle ABC, that lets you know what you're reflecting, and that is equal to the new image, triangle A prime, B prime, C prime. Those prime tick marks tell you that it is the image. The next thing we need to discuss is a rigid motion. A rigid motion is when we move an image or a shape or an object or anything, and it preserves the angle measure and the length. AKA it doesn't get bigger, it doesn't get smaller, and the angles don't change. So the length of the sides are the same and the angles on the inside are the same. Example 1 deals with that, so let's turn to it. Example 1 says, is each transformation a rigid motion? Explain. Just a reminder, rigid motion is a movement that preserves length and angle measure. So what I've done for us for part A is I have labeled the 4 points of this shape, and see if you can figure out how the pre-image points relate to the image points. Where does point A go? What happens to it? Well, this is what happens to our point A, so we call that A prime. Can you guys see that this shape has just been rotated? And then across from A prime would be B prime, and then down would be C prime, then over would be D prime. To where the pre-image was just rotated to get the image. And so the length and the angle measures are the same. So example A would be a rigid motion, yes, because length and angle measure are preserved. Look at part B. What do you notice between the pre-image and the image? It gets bigger. So no, that's not a rigid motion because the length and the angle measure were not preserved. Those sides are going to be longer. The angles might be similar, but the length of the sides are going to be longer. So it's not a rigid motion. We're just going to quickly talk about example 2. You don't even have to write it down because it says, what is the reflection of triangle LMN across the line N? And so what we're doing is we're just going to flip it because that's what a reflection is. And this is a really vague example. So this is what this would look like if we were to just reflect it across, where if we connected these two, that's perpendicular. If we connected those two, that would have to be perpendicular. And these two, that would have to be perpendicular. Now, I just did a little sketch, which is hard to do when we don't have a coordinate grid. So let's jump down to example 3, where we actually have points on a line, or points that make a shape, and we can discuss it. It says triangle ABC has vertices, and it gives you their 3 points. And it asks you, what are the coordinates of the vertices of A prime, B prime, C prime for each reflection? And part A tells us we're reflecting across the x-axis. Part B says we're reflecting across the y-axis. We could draw this, You totally could. You're going to notice you weren't given a graph. So there's probably a way to do this without drawing it. And there is. So without graphing, we're going to learn the algebraic rules for what happens when we reflect over the x-axis and the y-axis. There's a little shorthand trick of what we can do with those points. So you're going to take those notes on the left side where you have that column of note space. So some rules we need to learn. If we reflect across the x-axis, we symbolize it, we write it as capital R, reflection, across the x-axis, so sub smaller x-axis, which is what they have literally right here. And the coordinates that we're given, x comma y, simply just become x comma negative y. So reflecting across the x-axis, notice the x's stay the same, and the y, we do the opposite sign. So if we're going to do part A, you were given your 3 vertices, A, B, and C. And now we're going to do the reflection across the x-axis, where we keep the x the same, and we negate the y. So this was negative 5, 6. So it's going to be negative 5, negative 6. Keep the x, change the y. B was 1, negative 2. Keep the x, change the y. Was negative 2. The opposite of that is positive 2. C, negative 3, negative 4. Keep the x, change the y. That'd be a positive 4. And that's what happens when we reflect across the x-axis. So again, reflect x-axis, aka keep the x, change the y. Guess what? If we reflect across the y-axis, we're just going to do the opposite thing. We're going to write it as capital R, sub lower y-axis. So it doesn't, see how I'm still writing it big, but I'm making it noticeably below. So reflection across the y-axis is quite literally the just opposite. So here we reflected across the x-axis, we kept the x. Here we're reflecting across the y-axis, keep the y, negate the x. Negative x comma y. So let's do it. Our A value was negative 5 comma 6. So now change the x, that'd be positive 5. Keep the y, positive 6. B was 1, negative 2. Negate the x, keep the y. C was negative 3, negative 4. Flip the x, keep the y. So your shorthand, if you just want to remember something really easy, if you're reflecting across the x-axis, keep the x, change the other. If you're reflecting across the y-axis, keep the y, change the other. That makes these type of problems really quick and easy. Don't even need to graph it. Just look at the coordinates, and then you can immediately make one of them negative to find the other coordinate. Now there's some other things we can flip and reflect our graphs on that aren't the x or y axis. Sometimes we can reflect them across a certain line. So I'm going to do a little example with you that's not in your book, just to show you another rule to learn. And I'm going to have this little image here. We're going to do this before you do example 4, where triangle KML is reflected over some line to form triangle KML prime, K prime, M prime, L prime. We don't know yet what it was reflected over, but what I have for you is I'm going to write the coordinates, and we're going to see if we can figure out what the rule is and what happened. So K was at negative 3, positive 5. K prime is now at positive 5, negative 3. L was at x is 1, y is 3. L prime is now at x is 3, y is 1. M was at x is negative 5, y is 1. M prime is at x is 1, y is negative 5. Can you guys find the little trick that happened? The x and the y's were switched. So this is when you reflect across the line y equals x, which is that diagonal line right here. If we reflect across the line y equals x, we've got a nice and easy trick. We can write it as the reflection across the line y equals x, so sub y equals x, and our given coordinates x comma y become y comma x. We literally just flip them around. That is a great rule to write down on the left side of page 103 where you have space for notes. Write that down. You're going to need that rule later. Easy peasy. When it's y equals x, you just switch the x and y's. And now your try it problem for example 4, part A. It says, what is the reflection rule that maps each triangle to its image? And it gives you points C, D, E, and their reflected points C prime, D prime, E prime. So what I've done for us is I've put them on a graph. You don't need to graph these. But what I did do was I wrote them as 2 columns. So I just took the coordinates that we were given, wrote them as 2 columns, and see if we can figure out what happened. X was 3, y was 8. Then it became -8, -3. X was 5, y was 12. And then it became -12, -5. You guys noticing what's happening? X was 4, y was 6. Now it's -6, -4. What happened? We switched the x and y's and we made them negative. And that's if you reflect across the line y equals -x. That's a really bad straight line. But if we reflect across the line y equals -x, we can write it as reflection big R sub y equals -x. And your coordinates that you're given, x comma y, become -y, -x. And by negative, we just mean opposite sign. So if it was a negative, now it's positive. And those are 4 really easy reflection rules for if you're reflecting across the x-axis, y-axis, or either of these 2 diagonal lines. You don't even need to graph it. You can just use the coordinates, use the rules to find the new coordinates. But what happens when you are given a triangle, you're given the line of reflection, you're not given the new coordinates, and you are asked to find them? That's what we're going to do in part B. We're going to change up your problem just a little bit. That way you have an example of this as well. So what if you're given the coordinates and the line of reflection and you need to find the new points? We're actually going to use a graph. So I'll tell you right now, we're not going to do example 5, and there is a decent amount of space to the right of example 5 to draw a little x and y axis and graph these points. We're going to change up the problem. And you are going to see for part B, you're given your points F, G, H. We are not going to use the prime points, and I'm actually going to tell you that it's reflected across the line x equals 1. And what we're going to do is learn how to find those points by using a graph. So I'm going to hide them and cover them up right now. Because if we are given the initial starting points of our shape, our triangle, and we're given a horizontal side to side or vertical up and down line of reflection, we can easily reflect this line just by using a graph. So the first step is going to be to draw a dotted line or a highlighted line to represent the line of reflection, which is what I have here. We're going to have a line at x equals 1, which is on the x-axis at the value 1. This would be our y-axis. And we have our shape that we were given. We want to reflect it across that line, which means we're just going to flip it to the other side of the line. All we need to do is count the distance of each point to the line. So if I know how many it takes to get from F to this line, then I can go that many in the opposite direction, and that'll be my reflected F. And you guys, that's exactly what we're going to do. So I'm going to zoom in on this graph that I'm drawing and you're drawing somewhere in your thing. And we know that the point F was at the coordinate 7, 6. And we have our reflective line at x equals 1. So I'm going to count the points to get to the line. This is at 7, and we're going to go to 1. So that distance here is 6 units. That is way too thick. That's 6 units. So now, starting at x equals 1, I want to count 6 units in the opposite direction. So that's going to be 1, 2, 3, 4, 5, 6. And there's going to be my point f prime there, which is when x is -5 and y is 6. So f prime would be at -5, 6. And check it. That's what is given to you in the problem. That's f prime. And now you know how to find that. You're going to count that distance and reflect it. So let's find our other ones. Let's do g prime. G is down here. G is at 0, -4. So we're going to count the distance to the reflective line, which is just 1. And then we go 1 in the opposite direction. So that's going to be here would be g prime at 2, -4. 2, -4 for g prime. And now our last one is h prime. H was at -5, 0. So we want to count the distance to our reflective line, our line of reflection. And that's at -5. So this would be 1, 2, 3, 4, 5, 6. Now I'm going to go 6 in the opposite direction. 1, 2, 3, 4, 5, 6. Right here would be my h prime at 7, 0. And I could connect those dots, and you guys are going to see that we truly just reflected that triangle at that line at x equals 1. And so that is how, and that is the best way to find your new vertices, which is your points right here, when you are given a horizontal or a vertical line of reflection, is to just draw a little graph, count the points, and there you go. That is section 3.1, reflections.